All right, welcome. This is part two of dynamics. Then we're going to look at free body diagrams in friction. Okay, a free body diagram is a diagram that only shows forces on the body. So not forces that are acted by the body, but acted on the body. I abbreviated FBD because that's quicker to write. It's a free body diagram. Three examples. The first one is that if we had this hockey puck that's on ice, so it's assuming that there's no friction at this point, and the hockey stick is pushing on the puck, we have an applied force to the right, and we have weight that goes down and the normal force that we learned about going up. These two forces, the normal force and the gravity, are equal and opposite in direction, so they cancel each other out. But we do have an offset of forces after while the stick is on there, and so we're going to get an acceleration to the right. The motion will be to the right. So this is when we're pushing the puck. In the middle picture, that we're sliding but not pushing. So now the stick has passed, and we still have the weight and the normal force the same, but there are no other forces. And so in this case, the acceleration would be zero because there is no unbalance of forces. The motion will still be to the right. So you can't really tell from a picture unless it shows you there's motion, whether there's motion or whether this is standing still. On the third picture, if it comes across part of the ice that's got some friction, now because the motion is to the right, we have the friction to the left. So the friction is pushing back on the motion of the puck, and the acceleration will be to the left even though the motion's to the right. So from kinematics, you should remember that if the acceleration is opposite the motion, then it will slow it down and perhaps eventually stop it. So a free body diagram is a diagram just showing the forces on the object. So here's how we draw one. We take a mass. We normally just draw some sort of box. This could be any sort of object, but we try to minimize the fanciness of it by making the box. We do put the mass inside of the box and label it kilograms. Mass is not a force, although we just, for convenience sake, put the mass on the inside. Be sure you label it as the mass, though. So the first force that comes from the center of mass is the downward force, and this is the force due to gravity, and so we call that the weight. We label it force sub g to indicate that it is a force, and the g indicates that it's coming from gravity. But oftentimes we refer to that as weight. The opposite of that is the force that pushes up from the surface, and that force is known as the normal force, as you have learned. Normal indicates that it's perpendicular to the surface if it extended down to the surface. So normal force, F sub n. If you happen to have an applied force, you would also show that from the center of the mass, labeled FA to mean applied. You could be more specific on that. You could be the force of the boy or the force of the motor or something like that, but we're just going to call it an applied force. And then if there happens to be friction, that's going to go in the opposite direction, and we'll label that as F sub F. So those are all the forces on this mass. You could also, on your free body diagram, not only the arrows with arrowheads pointing in the direction they're going, not coming from, and the labels of the types of force, but you can also show where the motion is by putting a velocity vector. Because there's an imbalance of forces, we know there's an acceleration, so you can show that the acceleration is to the right. And then if you happen to have a displacement vector, you can show that down near the surface as labeled D. So the free body diagram, very simplistic, showing just forces, straight lines, arrowheads, labeled as such. If you have numbers for any of these, you could put the numbers in for that. Pardon me. Okay, so an example to draw a free body diagram is when we have a bowling ball that's in free fall. The only force that's acting on the body is the weight of the bowling ball, and that's directed downward. Another example is if we take that bowling ball and we're holding it, and now we have two forces. We have the weight also is still pulling down, but now we have an opposing force that holds it up. So this could be, this could also be rolling down the alley. It would look exactly the same. There's only one force if there's no friction. And then what we may have, though, is we may have a little bit of friction indicated by the left arrow, and because this would be the motion. So we have three other examples of a free body diagram. So to draw these, let's try these. You should try these on your notes. You can pause the video while you do that. So we have this boy pushing the box across the floor. Notice we don't draw the boy in there. We just draw a rectangle to indicate it's a box. It's at a constant speed. So we have an applied force because the boy is pushing. So we label that FA. And we have a friction in the opposite direction because it doesn't really say it's frictionless. But because it's constant speed, that frictional vector is equal to the applied vector, meaning they're the same thing. We do not have an imbalance of forces. Other forces in the free body diagram, of course, would be the weight pointing down and the normal force pointing up. You can indicate a direction of the speed because the friction's to the left, then the motion will be to the right. So that's how you would draw that free body diagram. The second example is if we have a worker pulling up on a bucket of paint from above. So of course we have this applied force by the worker going up, and we have the weight of the bucket pulling down. We do not have any sideways forces, so there's no friction, and doesn't indicate whether there's what the motion is. It says he's pulling it, doesn't say it's moving, doesn't say it's accelerating, so that's as much information as we can put on our diagram. So we don't really know of the motion. Okay, example is if we have this young lassie pushes a lad on ice skates that has a mass of 35 kilograms, and they push with a force of 60 newtons. What is the acceleration of the boy? So this is going to be an application of Newton's second law. So we're going to start our problem with Newton's second law, which is sigma F equals ma. How can I tell it's an application of Newton's second law? Well, a force is given and a mass is given, and it's asking for an acceleration. So you should know that Newton's second law is that. So at this point, I have 60 newtons. I'm in newtons and kilograms, so I have no conversions to do. I can simply, first I could solve for the acceleration. I can then put the values in. The force is 60, the mass is 35, and so it comes out to 1.7 meters per second squared. Incidentally, the middle formula is the one that's on the AP formula sheet. The sigma F equals ma is not. All it is on the formula sheet is a definition of acceleration in terms of force and mass. So 1.7 meters per second squared is the acceleration of the lad by the push. Next example is what force is required to accelerate your friend on a rolling chair, a total mass of 120 kilograms, so that they pass their they change their speed from rest to 12 meters per second in 4 seconds. So once again, well, first off, we're going to have to solve for acceleration. So before we can get on to Newton's second law, we have to know what acceleration is. Acceleration is defined as the change in velocity in time. So delta V is defined as the ending velocity minus the initial velocity over time. And so that you learn from kinematics. So we put the numbers in for that. 12 meters per second minus 0 divided by 4 seconds gives us 3 meters per second squared. We can then apply Newton's second law by putting in the 120 for the mass and the 3 meters per second squared, and that will give us a total of 360 newtons. So I deliberately did this because these are the measurements that you could actually make. We don't always have an accelerometer, but we can measure speed and time, and so that would be more reality. Okay, we're going to talk about friction now, very general, and then we'll do some calculations. Friction is a force that acts oppositely to the motion or the applied force. It depends on the type of surface that it's in contact with. So if it's a slick surface, there'll be less friction than if it's a rough surface. It does not depend on the surface area in contact. I'll have to show you some examples of that in class, and as you'll see from the mathematics, that there is no dependency on surface area within the math or in practicality. It's directly proportional to the normal force. So that as the normal force increases, so does the amount of friction. The formula for friction, you will need this, is F of F equals mu Fn. So this little letter right there, this is a Greek letter mu, and in physics, it stands for the coefficient of friction. Coefficient of friction. We'll look at particulars in an upcoming slide. Friction is not a vector equation since F and the friction and the normal force are perpendicular. And on a horizontal surface, the good news is the normal force is equal to the weight, mass times acceleration due to gravity. So that'll make the calculations easier for right now. And the friction, of course, acts parallel to the surface. So if the surface is horizontal, then friction is also horizontal. Okay, so there are two types of friction that we're going to deal with. The first is kinetic friction, which is a sliding friction. As the word kinetic indicates, there's a motion going on there, and so there's already a movement in the body, with the two bodies that are in friction with each other. And so we subscript the coefficient of friction with the letter K to indicate that it's the coefficient of kinetic friction. This is one type of friction. This is the friction to keep an object moving. The formula for that would be the force of friction is equal to mu K Fn, just like the one in the previous screen where we didn't have the subscript. So we put that in if we're dealing with both types of friction. The other type of friction is static friction. This is indicated with the subscript S, and so we call it the coefficient of static friction. This is the friction to get an object moving. So kinetic is already moving, and so it's just to overcome that friction, and static is to take an object that is not moving or static and to get it moving. So the static friction is always less than or equal to the product of the coefficient of static friction and the normal force. So these two formulas are very similar. All it is simply putting in the coefficient and using the proper coefficient on whether the object's moving or whether it's static or not moving. And then for the static, you would calculate what the maximum static friction is, and then anything below that would also be the force of static friction. What is interesting is that the static friction is always greater than the kinetic friction. It's always harder to get to start sliding, but it's easier to keep it going. All right, here's an example. And please pause the video so that you can do your own calculations and check them with me. A worker pushes a 75 kilogram box with a force of 350 newtons. What's the acceleration of the box if the coefficient of kinetic friction is 0.45? So we're given the mass, we're given the applied force, and we're given the coefficient of friction, and we're looking for the acceleration. So first, a free body diagram. We put all the proper numbers in there. Put the mass in the middle, Fg, Fn opposing each other, applied force arbitrarily to the right, and then friction opposing that. It's true that this arrow should be coming from the center, but I have this habit of putting the friction down by the surface. Either way, you can choose to do that. And so with the other problems we've done, we're going to use Newton's second law of motion, sigma F equals ma. You'll find that this is a common practice using that a lot. The sum of all forces, we'll deal with that. We do have mass, so we could put the mass number in there, and we're looking for acceleration. We have to figure out where we're going to put this 0.45. So think about the forces, the normal force and the weight cancel each other out, so we really don't even have to include those. We're only concerned about the applied force and the friction. So we just put in the applied force plus the friction, which is the sum of the forces that are in line with the acceleration. That's going to equal ma. The applied force, of course, we know that's the 350. The frictional force, well, we don't have a number already for that. It's not the 0.45, but we use the formula for friction, mu kinetic is equal to Fn. And because we know this is a horizontal surface, that Fn is equal to the weight, so we replace Fn with, that should be mg, sorry about the typo. So we put mg in place of the weight, which is equal to the normal force, and now we have all the pieces to put in there. We're given a 350, we have the coefficient, we know the mass, we know gravity, we know the mass again, and we're looking for acceleration. So we replace everything with numbers. Put 350 there, 0.4578. Don't forget to deal with that negative 9.8. Because this force is to the right and this one's to the left, yes, we're going to have to subtract those two forces. If you accidentally leave that out, or if you subtract a negative, which will actually add, you're going to be using friction as another applied force, and of course that's not correct. So then we do the math and calculate that to 0.26 meters per second squared. Before we do any of those calculations, put those numbers, always be sure that your units are in kilograms and newtons, and then you're safe to use your units of meters per second squared for the acceleration. All right. Okay, so here's our next example. We have an iron worker who pulls on a rope that's connected to a 160 kilogram iron rail and drags it at a constant speed. If the rope makes an angle at 35 degrees with the horizontal and the worker pulls with a force of 100 newtons, what is the coefficient of kinetic friction? Okay, so in the drawing you can see that I have the mass of the object, and then we have the applied force going up from the horizontal at 100 newtons. So let's finish our free body diagram. And so you can see that, of course, we have the normal force going up and the weight going down. Those are not opposing the motion. We have friction going against the motion because the motion will be going to the right. All right, and now the thing we're concerned about is this applied force. Not all of it goes towards making the motion. So we're only concerned about this horizontal component because the friction is horizontal. We only need the horizontal component. And I'll tell you, eventually we're going to need to use this vertical coefficient, or rather component, also because we have an up force there and we have to deal with the two up and down forces there. All right, so with any of these problems, you could probably guess that we are going to start with Newton's second law, sigma F equals ma, as we have for the entire week. Okay, so but right off we interpret this constant speed. What does that mean? That means the acceleration is equal to 0. Okay, so we can replace that and we can have that the sum of all forces is equal to 0 because 0 times mass is going to be 0. All right, no problem. So what are the forces that we're concerned with? Well, once again, the applied force in the horizontal direction and the friction. So we simply replace this sigma F with the component of the applied force in the horizontal motion minus the frictional force because it's in the opposite direction, and that's going to be equal 0. Well, algebraically, that means that those two forces are equal if I add friction to both sides. So I simply going to get the coefficient that I'm looking for from this friction force, and we just have to calculate that. Well, yes, that's true. So the frictional force is equal to mu Fn, as we learned in previously here. Okay, so it sounds like we just have to take the normal force and plug it in there, and we can get that. Well, not so fast. But because some of the force that's applied is also up and down, we actually have to deal with the normal force now, no longer just equal to the weight, but we have to subtract out the force that's the coefficient, rather the component of the applied force in the vertical. The reason why we're subtracting it out is because it's sort of lifting that object up, so there's not going to be as much friction. Okay, well, we can simply put in the numbers for that. So we know the weight, which is mg, 160 minus 9 or times 9.8, and then we subtract out the component 100 sine 35. Quickly, that calculation comes out to 1511. Okay, so now we can go back to our previous statement there, where fx or f a of x, the horizontal component, is equal to mu Fn, and we can now put in the normal force, which is 1511, and the component horizontally is 100 cosine 35, and now it's just simply a little algebra and calculator work. Multiply 100 cosine 35 is 81.9, and then we're going to move the 1511 over to the divided into the 8190, and voila, our coefficient comes out to 0.054. So what looked like a pretty straightforward problem gets a little complicated when we have upward forces that are applied also. Okay, if you have any questions, you can comment on the video or send me a message. Thank you very much for watching.